Hello everyone, my name is Anshdeep Singh Kapula. My registration ID is 20 BCE 0797. Today I'm going to talk about a phenomenon in quantum mechanics called quantum tunneling. Now, before we start on quantum tunneling, we should first know what quantum mechanics is. So, quantum mechanics is the study of subatomic particles and atoms. It is a fundamental theory in physics which tells us about how particles of such small stature behave in nature. Quantum mechanics is an integral part of our fundamental theories of all physics, and it is essential to study about quantum mechanics. So, quantum tunneling comes under quantum mechanics. So, what's quantum tunneling? Every small particle in the universe has a wave-like property, and the wavelength associated with it is given by the de Broglie hypothesis, which is its wavelength lambda is equal to h, the Planck's constant divided by its momentum. So as you can see on the screen, this is the wave function of a particle approaching a potential barrier. As it approaches the potential barrier, it transmits through the potential barrier and its amplitude is decreasing exponentially. Now, this potential barrier has an energy greater than the kinetic energy of the quantum particle. And as it goes through the barrier, its amplitude decreases and again it suddenly transmits to the other side of the potential barrier. Now, this is counterintuitive to the classical mechanics in our real world because when there is a ball thrown at a wall, we don't see the ball going through the wall. Instead, we see it getting reflected back to us. This is not the case in quantum mechanics. Now, to get an intuitive idea of how quantum tunneling works, let's have a look at the next slide. The slide which I'm sharing right now shows us a person trying to get a boulder over a hill. Now, to get this object, this huge object over to the other side of this elevation, we have an intuitive idea of what we have to do. We need to apply some energy to it so it goes above and then it rolls down automatically. So, in physics terms, we describe it as the potential energy that the boulder needs to overcome to get to the other side. To do this, an external force or some external energy needs to be applied to the boulder so it overcomes the potential energy that is required for it to go over there. But now this is completely different from what is happening in the quantum level, where we see to make an analogy, we can see the boulder running across the entire elevation without ever interacting with the potential energy. So it does not need to have an energy greater, it does not need to have a kinetic energy greater than the potential barrier's energy to get to the other side. But the only drawback is its amplitude is exponentially decreased. Now, quantum tunneling is made harder the more thick the barrier is, because since the amplitude or the wave function decreases exponentially as it goes through the barrier, it will come down to zero very rapidly, and the probability that we can find it on the other side of the potential barrier is less and less as the thickness goes more and more. For less thickness, we can have a higher probability of finding the object on the other side. Now, where is this quantum tunneling seen in nature? Quantum tunneling is seen in the decay of atoms, and more precisely, we can see it in alpha decay. Now, alpha decay is the emergence of an alpha particle from a radioactive nucleus. Now, how this alpha particle really comes out of this nucleus is quantum tunneling. Even though the probability of the alpha particle coming out of the nucleus is quite small, but there's so many atoms that are radioactive in a substance that there's a lot of alpha particles coming out of it anyway. So this is something that we see to see the phenomenon of quantum tunneling in nature. Now, where do humans use quantum tunneling for their advantage? Now, quantum tunneling is a key principle in a scanning tunneling microscope. In short, we can call it STM. Now, the scanning tunneling microscope has a really small metal strip at the end of the pillar that we can see in the animation here. This pillar is quite close to the substance that we need to check. Now, what the STM does is it is used to image the substance that is kept on the base, and this substance is quite small. So we to have a clear image of it, we need to make use of quantum particles and this quantum phenomenon, which is called quantum tunneling. So what happens is this: there's a electrical potential difference applied across the metal strip and the substance. And since there is a small gap between the two, the small gap can be called as the potential barrier that the electrons in the metal strip need to cross. Now, since we have our friendly phenomenon quantum tunneling, the electrons can tunnel through the metal strip to this substance that we need to image. And once the electron does tunnel to the other side, there's a current which flows through the entire circuit, and behind this setup there is a computer setup which provides a feedback loop, and since the current is being recorded, the image is also recorded in the computer. The advantage of using electrons is that electrons can be used to map each and every atom of this substance, and since an electron is much smaller than an atom, we can get the entire image of the substance, which we cannot get through other means such as a microscope or cameras. So this is how a tunneling microscope works, using the phenomenon of quantum tunneling. Thank you, everyone.